Well, thank you for joining me again. And this time we're going to sit down and we're going to have a chat. We're going to chat about this reaction and about this lab experiment before we even go in and actually talk about the lab experiment. Okay, so what I mean by that is that there's some terms, words, we need to learn vocabulary in order for this to go forward very smoothly. And the very first word that we need to learn is something called qualitative analysis. All right, what is qualitative analysis? Well, folks, that's what we're going to be doing. So we're going to have to know what qualitative analysis means if we're going to be doing qualitative analysis. And the reason that I'm saying this is because there is another field, and that other field is called quantitative analysis. Oh no, qualitative and quantitative? What do you mean? How do we determine the difference between the two? Well, here's the nice little trick that I like to use. Quantitative with the N means numbers. Numbers mean calculations. Calculations mean measurements. Oh, a lot of math. That's what quantitative is. Well, good news for you. We're not doing quantitative analysis in this lab. Instead, we're doing qualitative analysis. So, quantitative analysis would basically concern concentration work. Concentration work meaning in a laboratory, I'm given a sample. Someone wants to know, how much is it? How much is in it? And I go in and I calculate how much is actually present, and I provide them a number. That is quantitative analysis. This is the field that we're not going to focus on in this lab experiment. We don't care about quantitative analysis. What we want is qualitative analysis. And qualitative is simply observation-based. That's all, folks. Observation-based. So this is what we see. What is going on in the experiment? When we add these two things together, did it change color? When we added these two things together, did it generate some heat? When we added these two things together, did we get some smoke? If we added these two things together, did they give us bubbles? If we added these two things together, that is what qualitative analysis is all about. What can I see? What can I report as far as the way things feel, maybe smell, and what they look like? So we're doing qualitative analysis on group 3 cations. Oh gosh, what is all of that mess? Okay, well, here's the deal. If you've not taken a general chemistry class yet, that's fine. There are two things in the laboratory environment that are called cations and anions. This comes from the term ion, hence cation and an ion. Okay, well, that makes sense, right? Well, the definition of an ion on the periodic chart of the elements, we have a little metal, or we have a little element, a nonmetal, a metalloid. It doesn't really matter. If it comes from the periodic chart, well, this is the element form, or elemental form. However, things don't really stay in the elemental form all the time. They can go crazy, and they can do things on us. And what they can do is that some of these metals or nonmetals or metalloids can make a decision to do something with their electrons. Well, they could kick them out. You know, maybe the electron just lived in the house a little bit too long. Maybe that electron stayed up in the bedroom, played video games, never had a job, brought friends over, trashed the place, lucky to wash the sheets and wash the socks. Well, sooner or later, that atom is going to get annoyed. And that atom's going to look at that electron and it's going to say, out. Enough of this. You are gone. You're leaving. Bye-bye. See you later. And the electron leaves. Well, the electron carries a negative charge, doesn't it? So if the atom kicks out an electron, that atom kicks out a negative charge, and the atom becomes positively charged because of that. And that positively charged atom is called a cation. Look at the T. You'll see a positive, and that is a very quick and easy way to remember what a cation is. All right, well, some elements, they might not do that. Some elements might look at these electrons and say, oh, you poor thing. Oh, I feel so sorry for you. You're not wanted, or, you're just out and you feel like you have no place to go. And, I just want to kind of give you a good home. So they take them in. I mean, people are the same way. You want to bring your best friend over? Well, we got a spare bedroom. We'll just move them on in. I'm sure you know people like that. So if they take in the electron, what they do is that they gain the electron. So that atom gains a negative charge, which means that the atom will get an extra negative. And that means this atom turns into an anion, where N means negative. So a cation is going to be an atom that has a positive charge. And an anion is going to be an atom that has a negative charge, all due to how they handle their electrons. What do they believe in life? Do you kick them out when they turn 18? Or do you bring that person in as well as 15 best friends and let them live at your house and take advantage of you? That's the difference between the cation and the anion. Which one are you? Okay, so now that we know anion, cation definitions, I'm going to go back up here and look at group 3 cations. And now we know. We are looking at positively charged atoms in this lab experiment. Okay, well, where are most of those going to be located? Pretty easy. Here's going to be a quick, nasty drawing of a periodic chart. So here we go. And on the periodic chart, if you've taken a chemistry course, if not, perfectly fine again. I'm not going to take anything for assumption. I'm not going to assume anything. There's going to be a staircase that happens here down this diagonal. Kind of starts with aluminum. And if you just go over, down, over, down, over, down, over, down, one by one by one by one, you'll end up with the staircase that's right here. Everything to the right-hand side of this staircase is going to be classified as a non-metal, and everything to the right-hand or left-hand side of the staircase is going to be classified as a metal. Anything on the stairs, either above or below, folks, this is typically called a metalloid. Okay, and each one of these have different properties, and this is one of the reasons that the periodic chart is structured the way that it is. It's not just a random shape that we just created out of the blue just to make it look weird and strange and complicated. There's tremendous amount of organization in the chart, and this is one of them. So all of the metals are over on the left. All the non-metals are over on the right. The metalloids are on the steps of the staircase. Okay. So where am I headed with this? Well, the metal side to the left to the left, Beyonce. Everything in the box you own to the left. Okay, well, this left-hand side, on the metal side, these typically have the tendency to kick them out. 18, you're out on your own. I don't care if you're in college. I don't care if you're still in school. It's time for you to grow up. It's time for you to be an adult. It's time for you to take care of yourself, and away you go out the front door. Yay! Well, over on the right-hand side, those nonmetals, they have a tendency to gain electrons. They have a tendency to create negative charges. Oh, you poor thing, come on in. We'll give you a room. We'll give you a home. We'll feed you. We'll buy you all the clothes that you need. Oh, boo-hoo-hoo-hoo. That's what the nonmetals do. So over on the left-hand side, these metals, okay, well, we're talking of things like copper. It's over on this side. Sodium, lithium, zinc, chromium. The list goes on and on. That means that if these are going to do something with their electrons, they're going to have a tendency to kick them out and become positive charges. Well, sometimes they can kick out one kid. Sometimes they can kick out 2 kids. Sometimes they can kick out 3 kids. Sometimes they can kick out 4 kids. It really just depends on what they have available at the time. So we see a variation in the positive charge that can happen with some of the elements. And these variations are going to happen mostly in the transition area of the periodic chart. And that's what we call them transition, because they can change. So for instance, copper could be a +1 or copper could be a +2. All right? Sodium, well, sodium doesn't have a flip-floppity charge. And the reason is because sodium is in group 1 or the group 2, the alkali metal or alkaline earth metal. Those typically have one charge and only one charge, and that is it. They're very simplistic. A very tiny little family with maybe 1 or 2 kids, and that's it. The transitional period here in the periodic chart, or what I call the valley, have tons of metals that can create positive charges, that create cations, and these cations can vary in their charge. Sometimes they're +2, sometimes they're +4. Sometimes they're +2, sometimes they're +3. It really just depends on what type of family, particular type of family we have. Nonmetals, typically they gravitate toward one type and that's it. And metalloids, you never know really what they're going to do. It kind of varies and changes. Sometimes they're like a nut, sometimes they're not. That was the old Almond Joy commercial. So sometimes they're like a metal, and sometimes they're not. We just really don't know until we use them a little bit more. And that's a story for a different day. All right, so what we have here is a focus on group 3. Okay. So group 3 has nothing to do with the actual groups that are assigned on the periodic chart. Oh, no. Yeah, that's right. We have group 1 and group 2, group 3, group 4, group 5, group 6, group 7, group 8. You probably learned these if you've taken general chemistry as the alkali metal, alkaline earth metal, the chalcogen, the halogen, the noble gases, right? Those are the groups, or what we would call families. Well, group 1, group 2, group 3, group 4, group 5, in the qualitative world, it doesn't really correspond to that. So that's the number one confusion that people have. We say, we're going to do group 3 analysis, and they think, oh, well, we're only going to be working with group 3 atoms. No. That's not what we're talking about. We are grouping them in the qualitative analysis world based on their precipitation based on their solubility properties. That's what we're doing. So before we go further, we're going to have to understand what these solubility properties are going to be. And here is a solubility chart, maybe something similar to what you would see in a general chemistry course. So let's talk about these for a minute, just so that we can kind of get our bearings. Up here at the top, it says solubility rules. Number 1, a salt of ammonium, NH4, and group 1A are always soluble. Okay, well, what does that rule mean? Well, that means if I have an ammonium with something else, or if I have a group 1 from the periodic chart, not qualitative analysis world, from the periodic chart, these are my alkali metals. If I have something like that with something else attached to it, then all of these are going to be soluble. So here's a periodic chart. And what we're talking about, group 1. So group 1 is over here that starts with hydrogen. So that means if I have a lithium plus something else, a sodium plus something else, a potassium plus something else, rubidium plus something else, cesium plus something else, or francium plus something else, all of these plus something else will tend to be soluble. And again, what that means is that we have a substance that will dissolve in solution. We will not see a precipitate to form. Now, that's pretty important in the qualitative analysis world because that's what we're going to be playing off of. All right, now, number 2. Number 2 is going to say all chlorides are soluble, all bromides are soluble, all iodides are soluble, except for blah-blah-blah-blah-blah. Well, we have silver, mercury, and lead. For my bromides, we have silver, mercury, and lead. And then for the iodides, I have silver, mercury, and lead. So you mean to tell me that everything on the periodic chart, everything that we see here, if it is paired up with a chloride, which is there, or a bromide, which is here, or an iodide, which is here, if it is paired up with one of those 3, then they're all going to be soluble. Every one of them will be soluble. That means they stay in solution, except for mercury, number 80, right there, silver, Ag, which is number 47, right there, and lead. Can you find lead? I don't want to do all the work. Can you find lead off this periodic chart? Well, if you said number 82, that's where it's going to be. Number 82, PB, there's lead. So out of everything on the chart, those three little weird ones, silver, mercury, and lead, 47, 80, 82. If those pair up with a chloride, bromide, or iodide, then the solubility rules say that they precipitate out. They are insoluble. That's what that word means. Insoluble means it precipitates out. Right there it is. Well, folks, welcome to Group 1 of the qualitative world. So silver, mercury, and lead are going to be regarded as Group 1 cations. And the reason that they are in a group is because they behave unlike anything else when it concerns this solubility rule. Silver, mercury, and lead precipitate out the same way, and they all behave very, very common, except for everything else on the periodic chart, meaning that no other atom on the chart does what silver, mercury, and lead does with chloride, bromide, and iodide. But these three, even though they're different elements, even though there's different atoms that are involved, they all behave a similar way when it concerns the chloride, the bromide, or the iodides. And that is why we group them together, and qualitative world will regard these as group 1 cations. So this is where our term group comes into play in the qualitative analysis world. It is not to the periodic table. It's based on their reactions and based on their activity, depending on what we put them in. Now let's kind of go one down. Rule number 3 says chlorates, ClO3s, nitrates, NO3s, and acetates, CH3COO, are soluble. That means that they will dissolve in water, mainly. Okay, so chlorates and nitrates and acetates will all stay in solution. They will not precipitate out. And I've already kind of hinted, hint, precipitation is very important in qualitative. Number 4, sulfates, SO4s, are soluble, except calcium, strontium, barium, mercury, lead, silver, and those are insoluble. Oh, okay. So now we've kind of broadened what can precipitate out. If I take a look at rule number 4, calcium, strontium, barium, mercury, lead, silver. If there's sulfate that I put into that solution and it has those cations that are present, then the sulfates will grab those cations and drag them out of the solution for me. They form a precipitate. Well, up above in step number 2, it already talked about mercury and lead and silver, and it said that chlorides would do that. Yeah, they do. That's why we call them group 1. So mercury and lead and silver can be hit with chloride and they fall to the bottom of the tube as a precipitate. If I can remove those, it looks like sulfate, if it's added next, could grab calcium, strontium, and barium and make them fall to the bottom of the tube. Well, this is a very good sign that this is a different grouping, because no other cations will allow me to do that, right? I mean, sulfates are soluble. That means everything else on this periodic table, if it is hit with a sulfate, stays in solution. It's not going to precipitate out. The only ones that do that is calcium, strontium, and barium. Okay, so where are those? Calcium is right here. Number 20, calcium. Strontium, look at there. There's number 38, right on top of each other. And barium, look at this one, 56. Again, right on top of each other. They are clustered together right there in what we call group 2 or family 2 of the periodic chart. Well, does this mean that calcium, strontium, and barium would be classified as a different group in the qualitative analysis world? Maybe. We'll see that, but this is where I need your mind to be as we go through and talk about a qualitative analysis scheme. So, if I can, step 1, add chloride, I could remove the mercury and the lead and the silver. And in another step, if I add sulfate, then I could remove calcium and strontium and barium from a mixture. So let's keep going on. Let's keep looking at these solubility rules. Number 5, phosphates and carbonates are insoluble except for ammonium and group 1A. All right, so group 1A again, lithium, sodium, potassium, rubidium, cesium, francium. So if I had, let's go back, sodium or potassium. If I had a sodium or potassium phosphate, it stays in solution. A sodium or potassium carbonate, it stays in solution. A ammonium phosphate stays in solution. An ammonium carbonate stays in solution. But everything else will fall out because that product is insoluble. A precipitate would form, and I would see that falling out into my test tube. Number 6, all metallic oxides are insoluble, except for the ammonium and group 1As again. And that's kind of the tradition here. Ammonium and group 1As pretty much soluble with every single thing. They are not going to fall out. Very difficult for them to fall out unless we play some tricks in order to kind of coax them into precipitating and falling out into the solution. Very, very difficult for those. So metallic oxides, metallic means metal. So again, the staircase right here, there's boron and aluminum. That's where the staircase would start. So over, under, over, under, over, under, over, under. There we go. So everything to the left, alkali metals, alkaline earth metals in group 2. All of my valleys, which include the 2 bottoms, as well as my transition metals, which are in the middle, as well as what we call post-transition metals. Sometimes post-transition metals, there we are, metalloids. Those are going to be classified as metallic, and if they bond up with oxygen, those are metallic oxides. Those are insoluble. So for instance, MgO. Mg is a metal. It's right there, number 12. If that pairs up with oxygen to make magnesium oxide, it is an insoluble compound. If calcium pairs up with oxygen, it's insoluble. A precipitate would happen. Okay? If ruthenium pairs up with oxygen, that would be a oxide. It's a metallic oxide. It will precipitate out, and it will be insoluble. That is what that rule means. Number 7, all metallic hydroxides, which are OH groups, they are also insoluble except for ammonium and group 1A and group 2A from calcium down. Those are going to be soluble. So ammonium hydroxide, that will be soluble. No precipitate will happen. Something out of group 1. Okay, well, let's pick sodium again. All right, so if sodium pairs up with OH for sodium hydroxide, that is soluble in water. Group 2A calcium down. All right, so here's calcium and on down. So if I pick calcium and I pair it up with OH to give me calcium hydroxide, this will be soluble. It will stay dissolved in solution. All other hydroxides, though, they all behave the same way, and they are insoluble, which means a precipitate would form. And then finally, down here at number 8, all sulfides are insoluble, except ammonium, group 1A, and group 2A. Once again, ammonium, group 1A, group 2A, if they pair it with sulfur, stays in solution. Anything else paired up with sulfur, it will fall out in terms of a precipitate. Whew, well, that's a lot, right? I mean, here we are at 30-minute time block, and we haven't really even started talking about the lab yet. I'm just preempting what the lab is going to introduce to you. Oh, gosh, so what does this even mean? Well, let's take a look. So here's the lab document as you're going to see it. Now, we're probably not going to get you to do the entire qualitative scheme. There is a chance that we will. It just really depends on time. So I have uploaded the entire qualitative scheme just in case we tell you to do it. And it also gives me a chance to talk about the preliminary that happens before. The first page is going to start off with qualitative group 1 and 2. Okay, well, group 1 and group 2, what does that mean? That's not group 1, group 2 on the periodic chart. That's something different. Group 1, we've already said, was silver, lead, mercury. So what's group 2? Well, group 2 is going to be bismuth and copper in these directions. Now, if I go back, silver, mercury, lead are all three listed, right? And I told you that that was group 1. But if I take a look at the lab document, we've listed silver, but where is mercury and where is lead? Well, here's the story, folks. We don't like to use it. This is a health hazard. These are environmental hazards. We don't like to go through the extra hoops of taking care of silver waste, lead waste, and mercury waste. If we have to pick one out of these three just to do a group 1, we're going to pick silver because it's a little bit easier for us to take steps to clean it and to keep it and to dispose of it. The mercury and the lead, money, 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 money. That's what that takes in order to dispose of it the proper way. All right, so that's why you see silver listed, but that's why mercury and lead is not there. But it would be. It would be. Silver and lead and mercury are all in group 1. We just don't fool with mercury and the lead as much. And that's due to disposal and basically getting you to work with it. It's a health hazard as well. Now let's take a look at group 2, right? In the solubility chart, as we went on down, we're like, hey, sulfates are soluble except for calcium and strontium and barium. Okay, calcium and strontium and barium. Well, look at here. Not really yet. Not yet. Not quite. We're not there. Something else is in here. So we'll maybe see those a little bit later down the road. So group 2 is going to be something a little bit different. And group 2 in this scheme is going to focus on bismuth as well as copper. So here's how I want you to understand what you're getting ready to do. You have a beaker or a sample of solution. That solution could have multiple positives that are in this. It is cation alphabet soup. That's what this is. And it's our job to figure out what's in the alphabet soup. What is present? What is there? What is missing? That is the whole intention of qualitative analysis. So is silver present? If so, how do we know? Is bismuth present? Is copper present? If so, how do we know? And these are the steps that we have to take in order to get there. Up here at the top it says the known, 5 drops of each cation, and you mix them together. The reason we do a known is so that you know what a positive test is supposed to look like. So you know that they're there. You know that they're present. You put them there. You did it. So they should be positive in the test. And it tells you how to do them. 5 drops of each one of these into a test tube, and that is your known. You know that those are supposed to be positive. And then we're going to give you an unknown. And it says use 20 drops. If you had to start off here, you would use 20 drops of the unknown. And then we would test that along with the known in order to compare the test. Are they positive? Are they negative? So it looks like if I had this, what I would do is I would add 3 drops of 6 molar hydrochloric acid. Then I would put it into a centrifuge. We would centrifuge it down. Well, this is my chloride source. I know that silver, lead, and mercury are insoluble with chlorides and everything else will not be. So there is my first grouping, and this is group 1. Now, because we're not really working with silver or lead, if you see a precipitate here, there's a very good sign that that precipitate is going to be silver. But this is just a hunch. So what you will see down below are just confirmation tests. So if I see a solid, if I see a precipitate form, then I'm going to wash it. 6 drops of 6 molar ammonia to dissolve it. 6 molar of nitric acid until I get it to acidic. And if I get it to acidic and I see a white precipitate, that is confirmation that silver is there. There's group 1, folks. Group 2, that would focus on bismuth and copper. I add nitric acid. I evaporate it to slush. I add some water. I add ammonia to get it basic. I add hydrochloric to go back to acid. I put it in a hot bath. I add 12 drops of thioacetamide, which is stinky, stink. And then I add it into a hot bath. And then I centrifuge it again. And thioacetamide is a sulfur source. And that centrifuge step will zoom the precipitate all the way to the bottom of the tubes, and that precipitate will be a bismuth and or copper. One of those could be there. Both of those could be there. If there's a precipitate, then it's probably coming from one or the other or both. The liquid that comes off of the centrifuge tube, that would contain all of the other letters of the alphabet soup. So I'm not yet quite at group 3. So this would be group 1 test and group 2 test. We're focused on group 3 test. All right, so here's another page with group 1 and 2. I'm not going to go through this. You can follow the flow chart if you want to know more about group 1 and group 2, but we're not. This is about group 3, and that's where this page begins to start. So it looks like group 3, we're focused on a couple of metals right up here at the very top. Cobalt, nickel, iron, manganese, aluminum, chromium, and zinc. Okay, well, what do I do with it? Well, I'm going to add 2 drops of 6 molar hydrochloric and 8 drops of water to my known or to my unknown. And I'll do both of these at the same time. Then I'll add 8 drops of thioacetamide. Stinky, stink. And then I'm going to add drops of concentrated NH3 to basic. Now, I need you to understand that NH3 is a gas. So don't go around and say, where's the NH3? Okay, the NH3 is actually NH4OH. It is a liquid. It is ammonium hydroxide. That is what you're going to be using because that provides you the NH3 source, which is ammonia gas. We don't have ammonia gas tanks laying around in the lab. So NH4OH will be your ammonia source. So this is how it's different from group 2. We go to basic. So that means it needs to be on the basic side of the house as far as the pH is concerned. So we put it in a hot bath, we centrifuge this down, and we will get a solid. And those solids will come from 1, 2, 3, or all of the above. Nickel sulfide, cobalt sulfide, iron sulfide, manganese sulfide, aluminum hydroxide, chromium hydroxide, zinc sulfide. Now, these two are a little weird, but I think that you would know where those hydroxides are coming from because we are using ammonium hydroxide as a source. And we're also taking it to basic. Well, centrifuge basically means this would be the solid and this would be the liquid that sits up above. You do not need that liquid, so bloop, off it goes. You just discard it, get rid of it. If you want to do group 4 and group 5 test, then you would keep that liquid. But we're not going to do that in the experience that we're going to have. We're not going to do the full-blown qualitative analysis. But if you had to, group 4 and group 5 would be saved for later. Right, then we're going to take 10 drops of water and 1 drop of ammonium hydroxide again and wash it. So that means add this stuff to the solid, take a stirring rod and jigger it up. Jigger it. Really kind of mess it up there. Stir it up really well. And then put it back into the centrifuge and spin it back down. Well, that solid will still be there, hopefully, right? And if you get any liquid on the top, and you will, that liquid needs to be discarded. You do not need that liquid for our purpose in group 3. Well, this solid probably still isn't cleaned as much, and we need to start separating these cations from each other. So 7 drops of water and 2 drops of acid will come next. Then we spin it back down in a centrifuge, and we will get a solid. But this time, the solid will only come from nickel or cobalt. That's it. The liquid that we have above in our test tube will have all of the other cations that we had in there before. So we are now separating the cations from each other. So the nickel and the cobalt will be our precipitate. We need to figure out, do we have nickel? Do we have cobalt? Do we have both? Which one do we have? So we need to start taking steps in order to get closer to that point. Well, I'm going to take my solid. Once I pour the liquid off into a separate test tube, I'm going to have another test tube over here, right? I've got some liquid in it now. I'm going to take the solid. I'm going to add water and hydrochloric again. I'm going to centrifuge it down. I'll still be left with a precipitate. Don't really know which one is which yet. But the liquid that will be above the second time will need to be combined, just to make sure that I did pull all of the other cations off of the nickel and the cobalt. That's why I did that for a second time. So you're going to combine those solutions together into the same test tube. So the first washing goes up here in the test tube, and the second washing will go into the same test tube from up above. Right, now, I have the solid. That was from the centrifuge step. I'm going to add nitric acid, put it in a hot bath. It will dissolve. Add water. Add ammonium hydroxide until it goes basic, and then I centrifuge it down. When I centrifuge it, if I see any yellow precipitate, this is sulfur, get rid of it. After the centrifuge step, I'm going to separate the nickel and the cobalt. So 6 drops of solution will go into a test tube. I add 3 drops of nickel DMG, or DMG. That will form nickel DMG, which is a red precipitate. So if I see a red precipitate that forms, ding ding, nickel is present. I've just confirmed it. All right, well, I'll take the rest of the solution here, and I will put that into another test tube. I'm going to add hydrochloric to it. Then I'm going to add 5 drops of ammonium thiocyanate and 1 ml of acetone. There will be 2 layers that form at the interface. That's what you're seeing here. There will be a blue-green solution. And if you see that blue-green solution, this is the positive read for cobalt. So I will have to do this with my known, because I know that those will be positive and I know what to look for. And then I'll do it with my unknown, maybe at the same time, and compare that to the known to see if my unknown has nickel or cobalt in it. It might not have either one. It might have one, it might have the other, it might have both. I just don't know. I don't know what they're going to give me. Now, I can't go back. I can't forget about what was on the previous page. All of these other cations that were washed and combined, well, we're going to have to figure out which one of those are present. And we'll continue down the qualitative scheme in the same exact way in order to figure out if those are positive readouts or not. So I'll let you be the interpreter of the qualitative scheme. I don't want to kind of lead you all the way through it. You need to be able to read these very abbreviated, shortened directions and figure out what to do in these steps. It looks like I'm going to be hot bathing it again. It looks like I'm going to be centrifuging it again. It looks like I'm going to be getting some more precipitates that form and then keeping liquids on top of those precipitates into a different tube. It looks like I add more reagents, and then I'll look for colors, right? Purple and pink solutions, positive for manganese. Deep red solutions, positive for iron. Then I separate the aluminum and the chromium and the zinc from each other. All right, well, a colorless gel would be positive for aluminum. And then I need to separate chromium and zinc. And it looks like a yellow precipitate would be chromium, and a white precipitate would be zinc. All of these colors are going to be all wrapped up in the qualitative analysis scheme. Now, at the end of this lab document, you'll see group 4, and as you go through, you'll also see group 5. So group 4 and group 5 we probably will not do. We can. We've done them before in the past, right? We've got everything that we need to do with all of these, but just due to the sake of time, we're going to get you to focus on the heart of qualitative analysis, and that will be group 3, which actually includes most of the cations that are involved in the test. All right, so my advice to you is to go and print this off, read through it, make sure that you understand what these steps are telling you to do as you go forward. The other thing that I want to say is this idea of going to acid or going to basic. All right, well, we have two different types of acid paper in the lab, or pH paper in the lab, and one is called red litmus and the other one is called blue litmus. So blue litmus is a piece of paper that is blue, and red litmus is a piece of paper that is red. All right, so that's not too difficult, is it? No, nobody said this had to be difficult, right? It makes common sense sometimes, so there we go. So the purpose of red litmus, it's red because this paper is acidic right now. Nothing on it, it's acidic. And blue because blue is basic most of the time. And that blue piece of paper is a basic piece of paper. And when the directions say until basic or until acid, you have to be able to pick out the right paper. So what that means is that if we want something to go to basic, that means we want it to be basic. I can't use basic paper. Basic paper is already a base. If I go to basic and I'm using paper that's already basic, how are you going to do that? You can't. So what happens here is that I'll take a container, I'll dip a stirring rod down in it. I'll take a drop of that solution and I will put it onto the acidic paper. And if that paper turns a blue blob, blue means base, then ding ding, I've got a basic solution on my hand. That is how we use these papers in the laboratory, right? If I want to do something too acidic, I do it very similar. I'll take my sample, I'll put a test tube in it or a stirring rod in it, but I grab the blue litmus paper. The blue litmus paper right now is blue. That means base. I need to see if this has went acidic. So I put a drop of that solution on the paper, and if that drop goes red, then ding ding, that means that you are now acidic as far as your test tubes are concerned. So red litmus, blue litmus, that is what they mean. That is how we use them. Blue litmus means basic paper. You use it to see if your solution's acidic. The acid and the base react together. And if you get a red dot, then that means you have an acidic solution. If you had an acidic solution here and you try to put it on the acidic paper, it will make a red dot, but the paper's red, so you would never see the dot. You would just see red paper still. Okay, makes sense? The same thing happens with basic. If you want to see if something goes to basic, you're going to have to put a dot on acidic paper, and that will go blue if it is basic. If you put this solution on a basic piece of paper, well, if it's supposed to go blue and the paper's already blue, then how on earth are you going to see it? You can't. So keep these in line. Make notes of them if that's what you have to do till you get used to the concept, because it is quite tricky in the very beginning. So that's how we test if something goes too basic or if something goes too acidic. And you're going to see those statements scattered throughout the qualitative analysis scheme. So, for instance, right up here, add 6 molar hydrochloric acid to acid. That is what that means. You're going to keep adding this until you test it on a sheet of paper, and that paper goes red. And when it goes red, you are now acidic. And that is what that statement means. All right. So, maybe I've confused you more now than ever before, but qualitative analysis is what we call a gut. It is a gut lab, which means you've got to go into the lab, you've got to follow the directions, you've got to trust your gut, because there's no proper measurement, there's no proper, like, how precise do we have to be? You know, how can I read the graduated markings? I need to actually measure out the right amount of belt. No, it's none of that. It's add this stuff to a tube, tell me what it looks like, spin it down, separate it, write down your observations, and you're good to go. That's what this lab is all about. All right, so with that said, good luck. Before you get finished with the lab, you need to check your answers. And you need to check your answers because there is a probability that you will not be able to determine every single cation that you might have the proper way. So if we see a questionable point, like, no, you should have had this, you need to go back and maybe retry it. Then we'll have you to go back and retry it. And we might even watch you do it just to make sure that you're doing it the proper way. But do check your answers with the lab instructor before you leave for that particular day. Very important that you do that. So that way we know if you're doing the test the proper way or not. All right, so with that said, good luck in the lab. I think that out of everything so far, this is the one that you would need luck on because it's so wishy-washy at times, because it's not cut and dry, that a lot of people begin to mess up with the qualitative analysis scheme. So good luck, have fun, and I think that you'll enjoy the lab if you do. So I'll see you in the lab when that time comes, and we'll welcome you to the world of qualitative analysis.